Before atoms were neat diagrams in textbooks, they were mysteries, guesses wrapped in philosophy. Scientists thought atoms were solid, indivisible, almost boring. But one experiment, one bold question, and a few flying particles changed everything. Today, we step into the mind of the man who shattered the atom's old image and laid the groundwork for modern atomic physics. This is the story of how Ernest Rutherford built the foundation that every physicist still stands on. When I began my work, the atom was treated less as a physical object and more as a philosophical convenience. Many spoke of it with confidence, yet few had ever truly challenged its structure with experiment. The prevailing models were tidy and polite, designed to offend no established principle. They imagined the atom as a smooth sphere, its charge spread evenly, its interior calm and unremarkable. Such images were comforting, but comfort has never been a reliable guide to truth. As I often reminded my students, an alleged scientific discovery has no merit unless it can be explained to a barmaid. The earliest atomic ideas served chemistry well enough, but physics demands more than usefulness. It demands accuracy. Dalton's atom, indivisible and solid, explained chemical combination but said nothing of electricity or radiation. Thomson's model went further, embedding electrons in a positively charged body like fruit in a pudding. It was clever, even elegant, and for a time it satisfied many. Yet elegance is not evidence. These models described what atoms might do, not what atoms truly were, and they rested on assumptions that had never faced serious experimental resistance. What troubled me most was not that these models were wrong, but that they were untested in any meaningful way. They relied heavily on averages and indirect effects, avoiding direct confrontation with the atom itself. The atom was treated as something too small, too elusive to be probed decisively. I found this attitude unacceptable. Nature does not hide her secrets out of courtesy. She hides them until we devise the means to force an answer. Physics, I once said, is the only real science. The rest are just stamp collecting. Early atomic models also failed to account for the growing body of evidence emerging from studies of radioactivity. Alpha and beta particles were not abstractions. They were measurable, energetic, and defiant of neat theory. The existing models had no convincing explanation for how such powerful emissions could arise from a soft, diffuse atom. If positive charge were spread gently throughout the atom, how could it possibly repel a fast-moving alpha particle so violently? The mathematics faltered, and the physical picture grew increasingly strained. There was also the matter of scale. These models assumed that mass and charge were distributed in ways that felt intuitively reasonable to human minds accustomed to solid objects. But atoms are not obliged to respect human intuition. The more closely we examined atomic behavior, the more it became clear that our mental images were projections, not discoveries. We have to remember that what we observe is not nature herself, but nature exposed to our method of questioning. Without sharper questions, our answers remained vague and misleading. I became convinced that the failure of early atomic models lay not in a lack of intelligence, but in a lack of boldness. Too many theorists adjusted equations to preserve the picture they already liked. Too few were willing to risk destroying the picture altogether. Science progresses fastest when a cherished idea is placed directly in harm's way. If it survives, it deserves our respect. If it fails, it deserves to be discarded without sentiment. These limitations were not merely technical, they were philosophical. Early models assumed continuity where nature preferred concentration, smoothness where reality hid violence. They underestimated the possibility that most of the atom might be empty space, an idea so unsettling that few dared to entertain it seriously. Yet without considering such extremes, progress was impossible. As I often reflected, it is utterly impossible to be sure of anything, and that uncertainty is precisely what drives inquiry forward. Thus, before any new structure could be proposed, the old ones had to be confronted, not with words, but with particles, collisions, and measurable deflections. The atom needed to be challenged at its core, forced to reveal whether its charge was gentle or fierce, spread out or tightly bound, predictable or dangerous, and whether our comfortable pictures were anything more than shadows cast by ignorance. When we began the experiment that would later be called the gold foil experiment, there was no sense of drama in the room, only careful preparation and curiosity. I instructed my students to direct alpha particles at an extremely thin sheet of gold and observe how they scattered. The purpose was modest, to see whether the accepted atomic picture could survive a direct test. Alpha particles were ideal for this task because of their mass and speed. If anything substantial existed inside the atom, these particles would reveal it through their behavior. The setup itself was simple, almost deceptively so. A radioactive source emitted alpha particles toward the gold foil, and a fluorescent screen detected their impacts. Each tiny flash of light marked the arrival of a particle, allowing us to measure how far it had been deflected. According to existing expectations, nearly all particles should pass straight through with only slight deviations. Gold atoms, under the prevailing model, were thought to be too diffuse to cause any dramatic effect. At first, the results appeared to confirm what everyone believed. The majority of alpha particles traveled through the foil as if nothing were there, deviating only slightly from their original paths. This was reassuring, almost dull, and it would have been easy to stop there and declare the theory sound. But science does not advance by ignoring anomalies, and it was the rare events that caught my attention. A small fraction of particles behaved in a completely unexpected way. Instead of passing through or gently deflecting, they were scattered at large angles. Some even rebounded backward, returning toward the source from which they had been fired. These events were infrequent, but they were unmistakable. No amount of experimental error could account for them. Something inside the atom was exerting an enormous force on these alpha particles. I considered carefully what could cause such dramatic deflections. Alpha particles are heavy and positively charged, and to reverse their direction would require a force far greater than anything a diffuse cloud of charge could provide. The only plausible explanation was that the atom contained a region of extremely concentrated positive charge and mass. This region had to be very small because most particles pass through without incident, yet powerful enough to violently repel the few that came close. This realization forced me to abandon the comforting simplicity of the old atomic picture. The atom could no longer be imagined as a uniform sphere. Instead, it had to be mostly empty space, with its positive charge and mass confined to a tiny central core. The gold foil experiment did not merely suggest this conclusion, it demanded it. Any other interpretation failed to explain the observed scattering. The more I analyzed the data, the clearer the implications became. The probability of large angle scattering was directly related to how closely an alpha particle approached the central charge. This allowed me to estimate the size of the nucleus relative to the atom itself. The result was astonishing. The nucleus was thousands of times smaller than the atom, yet it contained nearly all of its mass. The atom, once thought to be compact and filled, was revealed as a vast emptiness, punctuated by a dense core. What struck me most was how such a simple experiment could expose such a profound truth. We had not shattered the atom physically, but conceptually. By observing how alpha particles scattered, we had mapped the invisible architecture of matter. The experiment transformed abstract speculation into concrete evidence, replacing assumption with measurement. This discovery did not arise from complexity, but from persistence and attention to detail. It required trusting the data even when it contradicted long-held beliefs. Many found the conclusions unsettling, and I understood their hesitation. To accept that matter is mostly empty space challenges intuition, yet the evidence left no room for compromise. Through the gold foil experiment, the atom revealed its inner structure not through words or equations alone, but through the silent testimony of deflected particles. Each unexpected flash on the screen was a message from the atomic interior, insisting that we rethink everything we believed about matter, charge, and the organization of the physical world. Once the evidence forced me to accept the existence of a concentrated center within the atom, the next task was to understand what this meant for atomic atomic structure as a whole. The idea of a nucleus was not simply an added feature to the atom, it completely redefined it. All previous models treated the atom as a broadly filled object, but the nuclear concept demanded a radical shift in scale, proportion, and force. The atom was no longer a small, solid thing, but a system dominated by a tiny, massive core surrounded by vast regions of space. The nucleus, as I conceived it, had to carry all the positive charge of the atom and nearly all of its mass. This conclusion followed directly from the scattering data. Only such a dense and powerful center could deflect alpha particles so sharply. The electrons, by contrast, contributed almost nothing to the atom's mass. They had to exist outside this nucleus, moving around it at relatively great distances. This separation of roles between nucleus and electrons was essential, for without it the experimental results could not be explained. What emerged was an atomic picture governed by extremes. At the center lay an incredibly small yet immensely dense nucleus. Around it extended a region that was almost entirely empty. The distances involved were staggering when considered proportionally. If the nucleus were reduced to the size of a grain of sand, the atom itself would stretch across a vast field. Matter, which feels solid to our senses, was revealed to be structured mostly from emptiness, a conclusion that challenged not only physics but common intuition. This nuclear atom also introduced a new understanding of atomic stability. The atom's mass was concentrated at the center, giving it a gravitational and electrical anchor. The electrons were bound to this nucleus by electrical attraction, forming a structured system rather than a diffuse mixture. Although my model did not yet explain how electrons moved without collapsing inward, it established the central problem clearly. By defining the nucleus, the question of electronic motion became unavoidable rather than hidden behind vague assumptions. The nuclear model also transformed our understanding of atomic interactions. Chemical behavior, previously treated as a surface phenomenon, now had to be interpreted in light of a deep internal structure. The identity of an element depended on the charge of its nucleus, not merely on the arrangement of electrons. This idea planted the seed for the concept of atomic number, which would later become fundamental to chemistry and nuclear physics alike. There was also an important implication for radioactivity itself. If atoms contain dense nuclei, then radioactive decay must originate there. The emission of alpha and beta particles could now be understood as nuclear events rather than superficial disturbances. The nucleus was not an inert core, but an active, dynamic entity capable of transformation. This realization opened an entirely new field of inquiry into nuclear processes, energy, and transmutation. I was aware that the nuclear atom raised as many questions as it answered. Classical physics struggled to explain how electrons could orbit a nucleus without losing energy. Yet I did not see this as a failure. On the contrary, defining the nucleus gave future physicists a precise target. A vague model cannot be refined, but a sharp one invites improvement. The nuclear atom provided a framework sturdy enough to be challenged and extended. What mattered most to me was that the atom had acquired an internal architecture grounded in experiment. No longer was it an abstract convenience. It was a structured system whose features could be inferred from measurable effects. The nucleus stood as the cornerstone of this structure, anchoring mass, charge, and identity in a single compact region. With the birth of the nuclear atom, the study of matter crossed a threshold. The atom was no longer indivisible in practice, nor simple in design. It became a complex system governed by forces of astonishing strength and scale. This conception did not merely adjust atomic theory, it reoriented physics toward the interior of matter, where the nucleus ruled as the defining feature of atomic existence. The recognition that the atom possessed a dense central nucleus forced a complete rethinking of how space itself functioned within matter. Previously, the atom had been imagined as a compact object, filled throughout with substance and charge. With the nuclear model, this image collapsed. The atom became an arena of vast internal distances, where particles moved through regions that were, for all practical purposes, empty. This was not a minor adjustment in scale, but a profound redefinition of what it meant for matter to occupy space. Once the nucleus was acknowledged as extremely small and massively concentrated, it followed that the majority of the atom's volume could not contain much of anything at all. The electrons, lightweight and few in number, occupied regions far from the nucleus, leaving enormous gaps between themselves and the central core. This meant that solidity, as experienced in everyday life, did not arise from filled space but from electromagnetic interactions. Objects did not resist one another because they were solid throughout, but because the forces between their atomic structures prevented overlap. This understanding altered how physicists thought about distance and separation at the smallest scales. The idea that particles could exist so far apart relative to their size challenged classical notions of compactness. The atom was revealed as a system defined more by forces than by physical contact. Space inside the atom was not passive emptiness, but an active region governed by electric fields extending outward from the nucleus, shaping the behavior of electrons and determining atomic interactions. By redefining atomic space, the nuclear model also reshaped our interpretation of motion within the atom. Electrons were no longer static features embedded in a background, but dynamic participants moving through largely empty regions under the influence of the nucleus. This conception demanded new ways of thinking about stability and motion. It was no longer enough to imagine electrons simply existing in place. Their paths, energies, and interactions became central problems that physics had to confront directly. The vast emptiness within the atom also provided an explanation for the penetrating power of radiation. Alpha particles, despite their mass, could pass through thin sheets of metal because they traveled through empty regions between nuclei. Only when they approached very close to a nucleus did strong forces act upon them. This insight unified scattering experiments with the internal structure of matter, showing that observed phenomena were direct consequences of atomic architecture rather than mysterious exceptions. This redefinition of space had consequences beyond atomic physics. It influenced how scientists thought about density, strength, and material properties. The realization that matter was mostly empty space suggested that changes in structure, rather than changes in substance, could lead to dramatic differences in behavior. It hinted that the forces holding atoms together were far more important than the matter filling them, a concept that would later echo throughout solid-state physics and quantum theory. Furthermore, the nuclear model reframed the question of scale in physics. The enormous difference between the size of the nucleus and the size of the atom introduced a hierarchy that demanded explanation. Why should nature choose such extreme separations? This question pushed physicists to consider new principles governing the small, where intuition derived from everyday experience could no longer be trusted. The atom became a gateway to a world where common sense failed and precision ruled. In redefining atomic structure, the nucleus transformed the atom from a simple object into a system with internal depth and complexity. Space within the atom was no longer an abstract concept, but a measurable, influential component of physical reality. The arrangement of this space determined how atoms interacted, how radiation behaved, and how matter itself could exist in stable forms. By exposing the emptiness at the heart of matter, the nuclear model compelled physics to confront a counterintuitive truth that what we perceive as solid is sustained by vast regions of nothingness structured by powerful forces. This realization did not diminish the atom, it enriched it, revealing a subtle and intricate organization that redefined our understanding of space, matter, and the invisible architecture underlying the physical world. When the concept of the nucleus entered physics, its influence extended far beyond the immediate explanation of scattering experiments. It reshaped the direction of scientific inquiry itself. Once it became clear that atoms possessed an internal core of immense density and charge, researchers could no longer treat matter as an indivisible whole. The nucleus provided a focal point around which new theories, experiments, and entire disciplines would develop, guiding physics into a deeper exploration of the material world. One of the most enduring consequences of the nuclear atom was the way it clarified the identity of elements. The charge of the nucleus emerged as the defining feature that distinguished one element from another. This insight laid the groundwork for the modern understanding of atomic number, replacing earlier classifications based on atomic weight alone. Chemistry, which had long relied on empirical rules, gained a firm physical foundation rooted in nuclear structure, allowing patterns in the periodic table to be understood as expressions of deeper order. The nuclear model also opened the door to quantum ideas that would soon follow. While my own work did not resolve the problem of electronic motion, it defined the problem so sharply that others could not ignore it. The need to explain how electrons behaved around a dense nucleus led directly to new principles governing energy, radiation, and stability. Without the nucleus as a central anchor, the quantum theory of the atom would have lacked both urgency and direction. Beyond theory, the discovery of the nucleus transformed experimental physics. New techniques were developed to probe atomic interiors, and increasingly energetic particles were used to explore nuclear behavior. What began as a study of atomic scattering evolved into nuclear physics, a field concerned with the forces, reactions, and transformations occurring at the heart of matter. The nucleus became not only a theoretical concept, but an experimental object, capable of being manipulated, split, and transformed. The implications of this work also reached into technology and society. Understanding the nucleus eventually made possible the release of nuclear energy, both constructive and destructive. While these developments lay far beyond my own experiments, they traced their lineage directly to the recognition that enormous energies were bound within atomic nuclei. The realization that matter itself stored such power altered humanity's relationship with the physical world, revealing possibilities that had once belonged to imagination alone. In education and scientific thinking, the nuclear atom changed how students and researchers approached fundamental questions. The atom was no longer presented as a simple unit, but as a layered structure with internal dynamics. This encouraged a mindset in which explanations were sought at deeper and deeper levels, fostering a culture of inquiry that refused to accept surface appearances as final truths. The nucleus became a symbol of the idea that nature often hides its most important features beneath layers of complexity. Perhaps most importantly, the nuclear model demonstrated the power of experiment to overturn established belief. It showed that even the most accepted ideas must remain vulnerable to evidence. This lesson extended beyond atomic physics, reinforcing the principle that scientific knowledge is provisional, always subject to refinement or replacement. The success of the nuclear atom was not merely in its accuracy, but in its willingness to challenge certainty. As the decades passed, the nucleus remained central to advances in physics, from particle interactions to cosmological processes. Stars, it was discovered, shine because of nuclear reactions in their cores, linking the smallest structures of matter to the largest structures in the universe. The same principles governing the nucleus helped explain phenomena on a cosmic scale, uniting different realms of physics under a shared framework. The legacy of the nuclear atom is therefore not confined to one experiment or one era. It persists as a foundation upon which modern physics continues to build, shaping how matter, energy, and the universe itself are understood. By revealing the nucleus, atomic physics gained a depth and coherence that continues to guide scientific exploration, influencing how questions are asked and how answers are pursued in the ongoing effort to understand the nature of reality.